Okay, so apologies for the abrupt ending in the last lecture. The good part was it was near about 50 minutes, so it happened then. But right now we can just continue from where we had left. Okay, so we had found out the strains due to sigma x alone, and now what we would do is a second sigma y is also present. Okay, so sigma x was acting, and over this we will now add a sigma y. Now let's see what this does. Consider a case, okay, I'm just drawing a 2D picture in which you have sigma x which was acting, and then you act sigma y. Now this will have its own strains which it has produced, and if there was a sigma y alone, it would have its own strains which it would have produced, and you would have been able to find it by the method which we have just gone through. Now this case in which you have both sigma x and sigma y acting, the claim is that because of the linearity of the stress-strain relationship, an increment of stress will always produce the same increment of strain regardless of the level of stress before the increment was added. So what sigma y will produce in this situation in which the sigma x was already acting will be the same as that sigma y would produce when there was no sigma x. Okay, so in this case you would have a epsilon y that would act as sigma y by E. Then you would have an epsilon x, and epsilon z is minus nu y and minus nu sigma y by E. So these are the additional strain components which would come into play because of this new sigma y, which is acting in addition to the existing sigma x. Okay, and you can think about it again, I mean from any thought process which appeals to you, that because of this linearity it wouldn't really matter. I mean, if sigma x was the strain what they will produce is independent of their each other. Okay, and you can similarly argue for a new sigma z as well. Now this sigma z will act in addition to this, so that will be sigma x, sigma y and sigma z. And what this sigma, the strains which this sigma z would produce would be there independent of whether sigma x or y, sigma y or sigma x and y exist, so they would be the same. Okay, so that is something which we have taken care of, and you clearly know that sigma y and sigma z will not produce any shear strains. Okay. Okay, so we have to include one other argument to, let's write it down, to rule out the possibility of a strain epsilon y due to stress tau zx. So just like a normal stress does not give rise to a shear strain, we have to also find out a way to say that a shear stress does not give rise to a normal strain. Okay, that is what we are trying to do over here. You can read this line once. So let's see how that can be proved, and we'll use similar arguments as before, so it should be easy to catch on. Okay, now if you see the rotation, so figure 5.15a, so this is a hypothetical normal strain due to a shear stress. So where is the shear stress acting? You have tau zx acting. Let's see whether it is actually tau zx. Okay, tau xz, tau zx, whatever name you would want to give it. Okay, so it acts on the z plane in the x direction. So this is tau zx and so on. Okay, so that's there, and this should ideally be written in theoretically as tau xz because it acts on the x plane in the x direction. But because tau xz and tau zx are same, I think we'll live with it. And why was the same, recall? Because the moments about the center were balanced, and the strains were gamma x z was the same as gamma z x, gamma x z was the same as gamma z x because of the geometry which we had seen in those diagrams. So the reasons were different. Okay, now these are the hypothetical normal strains. Where is the hypothetical normal strain? EY, okay, somewhere over there, epsilon y, and the stresses are given. So let's see what that, I mean, this is a question mark I am putting, right, because it is hypothetical. Let me just not make it real one. Okay, now the rotation of this by 180 degree, but now the rotation has happened about this axis. Please look at this. It seems it's an axis passing through the origin and at an angle of 45 degrees from z. Okay, so this is the angle through which this is passing through, and you are rotating it by 180 degrees. So in this case, your A would come up, D would go down, correct? Let's see what would happen to E. So if E is over here, E would come all the way to here, so that's true. B would again get rotated over here and so on. Okay, so if this is what has happened, so what is and then what should be the hold on, I think the way they have shown in your textbook, it is actually is it the strain in the y direction? I'm not really sure about it. Okay, because the way this I mean these extensions have been shown, it seems to be a strain in the z direction, a normal strain in the z direction. Okay, so it seems that this is what is happening over here. Okay, so I think this is actually epsilon z, and you would want to show that the, so please make this correction in your textbook. Okay, so this is actually epsilon z, and just because, I mean, you can see these how these projections are coming out, and it's in the z direction, and so this is the, and this is a question mark. Okay, just like we had this over here, these projections were showing the strain, and the same would happen. The point is, it is still a normal strain. Okay, so let's start with that. So once that is done, and once the rotation is done, now you see the points, the way they have moved, A over here, D over here, and E over here, and F over here, the strains have now actually, the sense has changed. So earlier they were extending in the x direction, now they are extending in the, earlier they were extending in the z direction, now you see they are extending in the x direction. And because the loading has not changed, this cannot happen in an isotropic material. So for this to happen, you cannot have a normal strain which acts. Okay, so you couldn't have had this Ez over here, and you can make a similar argument for uh, epsilon y. How you can do that? What you do is, I mean, ignore these dashed lines, and instead assume that there is a normal strain like this. Okay, in the epsilon y direction, you use the same arguments. Okay, and this would now get rotated by 180 degree. Where would it go? I think it would try to point in a direction which is different, very likely z if I'm not wrong, but you should check that. So this way you can prove that epsilon y is also 0. Okay, so you can show that for a tau z present, tau zx present, there is no epsilon x, no epsilon y, and no epsilon z. All three of them will be absent. So the only components on which this can depend is the shear strains. Okay, now more generally we conclude that a similar argument. So this is the first thing, that the normal strains will not be there for this tau zx. Okay, so similar symmetry and linearity arguments should show that no strain components other than gamma zx can exist. Now there is one more trick to this. It's not just that the normal strains will be absent. You want to also show that gamma xy for this case. Okay, this case, gamma xy and gamma yz will also be 0. How would you go about doing it? I am only discussing the start of it, but you should make this through. So let's start with gamma xz. So just ignore these dashed lines for a moment because they were showing the normal strains. Okay, and okay, so you want to now take care of gamma xy that would be acting on the x plane in the y direction. So let's assume that there is a rotation like this. Okay, so this line has actually become like this, and this line has become like this. Okay, so this is your assumed hypothetical gamma xy, and then the question is, how should you rotate to be able to make the conclusion that gamma xy is actually equal to 0? Okay, so please do this exercise. This is the only way to ensure that you have actually understood this. So the question is, you want to prove that gamma xy and gamma yz is 0. So for gamma xy, you have to consider a shear strain, like hypothetical shear strain like this. And then my question then would be, how should the axis, what should be the axis about which a rotation must be made in order to prove that gamma xy will be equal to 0? And you would then do the same for gamma yz. So you should be eventually able to show that gamma zx only depends, sorry, tau zx only depends on gamma zx, and then there is a linear, because it is the relationship is linear. I mean, you have killed practically all possibilities. So look at this. This stress was linearly related to all other components of strain. So that would mean that you have C1 sigma x, sorry, C1 epsilon x plus C2 epsilon y plus C3 epsilon z plus C4 gamma xy plus C5 gamma yz plus C6 gamma xz. So you have already shown that this is 0, this is 0, this is 0, this you will show that this is 0, this you will show that this is 0. See, the only thing left out is this. The stress is proportional to the strain, but unfortunately all the other 5 components of strain are 0 in this case, and hence the only possibility is that it would depend on gamma xz. So you write gamma xz as tau zx by this constant g, and this is called the g is called the shear modulus. It is also a material property, meaning it depends on the material, not on the size of the specimen which you have taken. Okay, and similarly you would have by similar arguments you can have gamma xy. I mean, you would repeat this whole analysis for a shear stress tau xy, and you will get that gamma xy is equal to tau xy by g, and a third analysis would be to gamma, sorry, okay. So that's how you would find out the effect of the rule out the possibility of all strains other than that exact corresponding strain for the shear stresses. Okay, now you consider a linear elastic isotropic, and then now you see how this isotropy is so important, right? I mean, isotropy helped you prove so many things by contradiction. So that's why this word isotropic is there. And linear elasticity, why is there? Well, because of this. Every component of stress is linearly related to every other component of strain. Now what you do, you have to consider now a case in which you have an element which has all the stress components acting. It has sigma x acting, it has sigma y, it has sigma z, it has tau x y, it has tau x z, it has tau y z, all 6 of them acting. And what would they do? Just like in the previous cases, they would individually, they would add the strain components which they would have individually applied alone themselves. Okay, so epsilon x, for example, would have been produced by, let's see the first case. First case was epsilon x was produced, where did it go? Over here. Okay, so epsilon x would have a sigma x by e. Okay, then what is the next term? For sigma y, epsilon x would be equal to minus of this value. Okay, so that would be minus of nu sigma y by e, and then again because of sigma z which is acting, you would have a minus nu sigma z by e. Okay, then same you would write for epsilon y and epsilon z, not writing again, but gamma xy would be only there because of this. It would not have any other contribution, right? So gamma xy will not have a contribution from, say, sigma x, sigma y, sigma z, and tau xz and tau yz. All of them will not contribute anything, and we have seen all these arguments. So this equation, this set of 6 equation 5.2 is called the generalized Hooke's law. What it tells you is the relationship between stress and strain in a 3-dimensional case. Okay, and you notice it is written in terms of material properties, which is this E, nu and G. All three of them are employed in writing this generalized Hooke's law. Okay. So this is where we are right away. So let me just okay, I don't know. Okay, we'll find out a way. So do note that we have written the generalized Hooke's law, which is equation 5.2, in terms of these 3 constants. At this time, this is a note which you should be able to make. Now let's see how to proceed further. Now the author in the textbook says in the next paragraph that as may be seen from the above equations for the shear strain, look at the equations of shear strain, gamma xy, okay, this is the equation of shear strain 1, maybe let me use another color, okay. So this is the equation of shear strains in the generalized Hooke's law, okay, the green ones. Okay, now as may be seen from the above equations for the shear strains, a consequence of isotropy, okay, this has come up because of isotropy, because of the arguments which we made for the symmetry and so on. A consequence of the isotropy is the fact that the principal axis of strain at a point of a stressed body coincide with the principal axis of stress at that body. Okay, very big words, huh? So let's repeat this statement once more, and this is something which requires you to actually think more about it. And I'll write the statement. So you have, say, sigma x tau x y tau x z tau yx sigma y tau yz tau zx tau zy and sigma z. This is, say, the state of stress at a point, okay, and you now convert it to the principal system using Moore's circle or using the eigenvalue theorem which you have learnt in maths, and what you would get is the principal values, which is sigma 1 0 0 0, sigma 2 0 0 0, sigma 3, right? There would be no shear stress in this principal stress components. So you have made, the idea is that you have made a certain rotation of the coordinate system, after which the stress in that coordinate system can be aligned like this, so that there is no other stress components other than these 3 normal stresses, and sigma 1, sigma 2 and sigma 3 are called the principal values of this principal stresses. And a similar thing you have done when you did a rotation. Also, let me just write it, epsilon x, epsilon xy, epsilon xz, epsilon yx, epsilon y, epsilon yz, epsilon zx, epsilon zy, epsilon z. This also you have done a rotation again separately, right? The theories of stress and strain are separate. So as of now, there is no, I mean, we have seen that there is a relation which we have just learned, the green ones over here. But what this has become is E1, E2, E3 and 0, 0, 0, 0, 0, 0. Okay? By a certain rotation. So let's call this rotation as R2 and let's call this rotation as R1. And the principal axis are, for example, principal axis of the stress would be, say, in the direction 1 and in the direction 2 and in the direction 3, and let me just use Roman numerals over here. Okay, just so that we don't confuse. So 1, 2 and 3 are the principal directions for stress. Okay, and 1, 2 and 3 are the principal directions of strains. Okay, this point is clear. I mean, this does not, this was coming up from the previous chapters. Now it is said that because of these green relationships which you see between the shear stress and the shear strains, and I mean the isotropy, I mean this relationships had come because of the isotropy. The fact that the principal axis of strain at a point of a stress body coincide with the principal axis of stress at that body. So, meaning 1 and 1 coincide, 2 and 2 coincide, and 3 and 3 coincide. Because of this. So how is the question which you must how is the question? I mean, why are they coinciding? Because of these relations. Can you think of a way? See, I mean, if you recall how you were, I mean, one is the Morse circle method, which you have learned from this book, and you should be able to think about it. Can you recall how you were finding the principal values, the eigenvalues, and the eigendirections? So, was it something like this? Okay, this was the characteristic equation. Okay, sigma was the principal value, I was the identity matrix, n was the orientation of this plane, the new plane which you have taken. Okay, and once you solve, I mean, I think the argument which you make it is that if this is to have a non-trivial solution, then the determinant of this has to be equal to 0. Okay, determinant of this particular thing has to be equal to 0. So how would you go about it? You have this sigma already, okay, and minus sigma I, sigma into identity matrix would mean that you have sigma x minus sigma sig tau xy, tau xz, tau yx, sigma y minus sigma tau yz, then you have tau zx, tau zy, sigma z minus sigma. This determinant has to be equal to 0. Okay, and that would give you what? It would give you these three principal values. So this will be a cubic equation in sigma, and you will get sigma 1, sigma 2 and sigma 3. This I am following the method of your maths too. Please don't stop at this method. You must find to make this conclusion from Morse circle as well. That's your responsibility. I'm showing you the non-trivial part. You should be able to do the easier part. Okay, so this will give you sigma 1, sigma 2 and sigma 3, and then what you have to do, you have to find the directions of n1, n2 and n3. Okay, so n1, n2 and n3 are the directions n1, n2 and n3, and that you would get by putting say sigma 1 into this equation back. You should be able to get what that the direction which is corresponding to sigma 1. You put sigma 2 into this, you will get a direction n2 corresponding to that, and those n1, n2, n3 are the directions of those principal stresses. Okay, you would do the exact same thing over there. Now because this are actually only related to this and this separately and this separately, you will be easily able to show that the directions 1 and 2 which you get, one of the Arabic and two or Indian, I mean one of the Indian and one of the Roman, will be the same. So this is something which you can do yourself, and please let me know if there is a problem which you face. Should be easy, but definitely you will have to open up your maths 2 or the linear algebra book and learn about it. The other way you should be able to make this conclusion is using Morse circle. So you have to do both of them, and if you face any doubt in either of them, please do it to a stage where you can do, and then approach me and I'll help you get there further. Okay, so please take it as an exercise for yourselves. Okay, let's change the color back to this one. Okay, now there is one more piece of information which the isotropy of the material can give, and that's what we would discuss now. So far in developing the stress strain equations, we have only made use of the fact that the properties of the material are the same in three orthogonal directions x, y and z. Okay, so a further relation between the elastic constants can be found from the fact that the material has the same properties referred to any set of coordinate axes. So we really used it along the x, y and z directions only, this property of isotropy, and said for the sake of arguments that the strains have to have the same response for isotropy, sense and the magnitude both. But in reality, isotropy is not constrained to 1, 2 or 3 directions. It is constrained, it is free to show, I mean it will show the same properties, same response along any directions or any axis. So to illustrate this, we begin by considering a state of pure shear as shown in figure 5.6. So this is pure shear. Okay, 5.16 I'm sorry. Okay, and using 5.2, the equation, the Hooke's law which we have just derived above, we can write for this pure shear, you can write that gamma xy, the strain, will be equal to tau by g. Okay, so it's a pure shear case, and the shear strain due to this will be equal to tau by g. I mean, know that. Now it is possible to obtain another expression for gamma xy, and what would that be? So to do this, we would want to proceed with a different way. So let's just do that once. Okay, so the stress components tau is equivalent to a principal state of stress with component sigma 1 is equal to tau. So look at this diagram. First of all, what is the state of stress for a pure shear, that's 0 tau tau 0. Okay, for this figure this is the state of stress. Okay, now we want to write this, and for this you have found out what the shear strain would be over here using Hooke's law. Now you want to find another expression for tau xy in a manner which is indicated to you like this. The stress component tau is equivalent to a principal state of stress with component sigma 1 is equal to tau and sigma 2 is equal to minus tau. Okay, sorry. Okay, so this, look at this particular figure. What you have done over here is for 1 in the sigma 1 you can write it as tau. Okay, in this case, I mean in this figure sigma 1 is tau and sigma 2 is what, minus tau. Okay, and this has happened because of this change, I mean this new geometry which you are seeing and the new loading as well, right? This was pure shear and clearly this is some sort of a biaxial normal loading. There is no shear component in this. Okay, now what does this do to the way we write the strains? So let's see, the principal strains refer to these axes in the E1 direction. Okay, what would that be? It would be sigma 1 by E clearly minus nu by sigma 2 by E. Okay, how do we write this? You have to apply the Hooke's law on this figure, in which now your one direction and two directions are shown and you have these nice orientations, so that, I mean it's not, it's very easy. Okay, and similarly you would have epsilon 2 that would be equal to sigma 2 by E minus nu by sigma 1 by E. Okay, so you have found the principal strains in this along these axes, and these are the values just by using the Hooke's law. And you can just substitute the value of sigma 1. I mean sigma 1 is tau, sigma 2 is equal to minus tau, so this would be tau into 1 plus nu by E, and this would be tau minus tau, I'm sorry, 1 plus nu by E. Okay, so sigma 2 is 0. So in your textbook I think epsilon 2 has a separate, an extra tau which you can remove. Okay, so you have found out these values. Now upon use of the strain transformation formulas, we can express the shearing strain with respect to the xy axis in terms of the principal strain. So what you do now is, for this 1 and 2 you have found out what the strains are. So you have, say, E1 0, 0 and epsilon 2. You must now rotate by 45 degrees, okay, to find the gamma xy. So if you rotate this by 45 degrees, I mean, and there are expressions, if you can go back to chapter 4, there is an expression of how to rotate from one coordinate system to the other. So think of this as 1, 2 as your present coordinate system, and then you want to rotate in a new coordinate system. So you would have x, epsilon y and gamma xy. So how would that happen? You can also do it using Morse circle, whatever way it works. So you will have this expression, and this gamma xy, when you do this, you will be able to get epsilon 1 minus epsilon 2. Okay, so that's how you would be doing this. So let me just check back what the gamma was. Yes, So you have to check equation 4.41. In that you have a gamma x dash y dash by 2, and that is equal to ex minus ey by 2 sine 2 theta plus gamma xy by 2 sine 2 theta. The only difference is in this the x will be equal to 1, y will be equal to 2. So sine 2 theta will be equal to 1 because theta is 45 degree, and gamma xy is equal to 0 because in the principal strain system the gamma 1 2 is equal to 0. So hence you have this gamma xy is equal to epsilon 1 minus epsilon 2. Okay, so that is what is equation B in your textbook, and you can write it, and this gives you a value which is equal to 2 times of 1 plus nu by E into tau. Okay, so once this is done, you can let's see how are you getting epsilon 1. Oh, so you are just substituting it from over here. Okay, so there's a minus sign already, so this becomes this. Now you already know what gamma tau xy was, and you have just written it in a new way using a new method, but they are the same strain values for a given state of stress. So what you would do is you would equate tau by g is equal to 2 times of 1 plus nu tau by E, and the tau's, because tau is not equal to 0, can get cancelled, and you will get g is equal to E by 2 into 1 plus nu. So remember we had written the Hooke's law in terms of these three constants E, nu and g, but it seems that they are not independent. So the third one can be written in terms of the first two. So this is the truth about isotropy, that you have only two independent elastic constants. Now you can call them E or nu, or you can call them nu ng, or you can call them E and g, or any other term which you might learn later or some point in any other course. But you will only have two elastic constants for an isotropic solid. So one thing which is not done, and that note has been made, I mean you have only done it say for gamma xy, okay, and you have like done this. Even if you do it for any other choice of coordinate system and any other choice of strain, it will still give you the same result. So that part is not done over here, but that is being told to you. So rather than considering gamma xy, you could have done any other component, you would have come up with the same thing. And even now, one thing which you have also noted, that we have, well, we said that it should have, the property should be same along any orientation, but what we eventually did was we only took a 45 degree. Well, the answer is, I mean you can actually do it for any choice of coordinate axis, but you will still get the same answer. The reason we took 45 degrees was because then this term would be quite easy. Okay, so that is why we took a 45 degree situation, but it's not shown to you, but you can just keep on doing for whatever angles, and it is. So this is the way we learn about this at in this point of our course. Whenever you take up say any advanced course in linear elasticity, mostly the postgraduate level courses, all this can be easily done using mathematics. Okay, here in this course you see we rely a lot on the forces and the equilibrium and the geometries and the symmetries. The reason being that these things are easier to visualize. You can see them, when you can feel the strain and the stresses acting on a plane in a certain direction. In the advanced courses, this visualization goes away. Okay, that also has its advantage in the sense if you want to code, so that format, that mathematics format is much more easier to implement in a code. This format is much easier if you want to think about experiments, or you want to really devise a setup to do something more hands-on stuff. So this is something which is more useful, and for the industrial perspective also this is quite important. This gives you a much better feel of the stress or strain than the other method. Okay, so it is not necessary, first of all, that every elastic material will be isotropic. Like bone or wood is another example. It is linear elastic, but it is not isotropic. It is anisotropic. So it is not. So we are considering the most simplistic case in which there is a linear elasticity and isotropy, but they are completely independent as such concepts. Okay, so that is where we sort of end this particular topic, and we'll have to make way for thermal strain, which is perhaps the last topic of this class. So for this, I'll get rid of this parts because so that I can write things over here. It already exists in the recording, so I mean, even when I rub it, I think you have access to it. Okay, so the topic which is left out is called thermal strains. So you already first of all know that, I mean, if you heat an object, most of them increase in size, and because there is a change in the dimensions, the deformation happens, there is strain present. So that is first of all the basic origin of this. But let's see how we can approach this in a slightly more rigorous way. In the elastic region, okay, in the linear elastic region, the effect of temperature on strain appears in two ways. How does the effect of temperature on strain happens? First is by causing a modification in the values of elastic constant. So for example, E, which we had taken, might depend on temperature. Nu might depend on temperature. Okay, and hence automatically G will also depend on temperature. So that's the first way that temperature can change deformation. Okay, the second is by directly producing something called a thermal strain. Okay, so one of the things which has been experimentally observed, that even when you change the temperature say by 100 degrees, the value of E and nu will change only very slightly. So the sensitivity of this on very large changes in temperature is very low. So what we usually do is we ignore this first part of it. And you know how why changing E would change the deformation, right? Because the strain depends on the stress and the temperature, and when the temperature changes, these values will change, and because the strains are linearly related to the stresses will change, and so all of that happens over there. Okay, so we'll only consider this part and the direct production of deformations in the solid due to temperature change. So one of the things is that this happens in the absence of mechanical stress. Okay, so there is only thermal loading as such. You don't physically apply any load, there is only thermal loading, in the sense there is only change in temperature, and that you can just show by this symbol epsilon T with T in the superscript. Okay, so for an isotropic material, the symmetry arguments show that the thermal strain must be a pure extension or contraction with no shear strain components referred to any set of the axis. So if you have a piece of solid and then it goes from temperature T naught to a temperature T, no other mechanical load acts. In this case, you will only have an axial strain, say Ex of T, Ey of T, Ez of T, and you already know this perhaps from our earlier knowledge, and that would be equal to alpha of T minus T naught. There would not be any. shear strains because of this thermal effects. And the reason for this is clearly isotropy. So no other reason. I mean, the same arguments which we have used before, we can use over here to find out. So this is what they mean, and that's how you would find alpha. You know is what? Alpha is the coefficient of linear expansion, and that is already known to us. Now just to tell you, I mean, in reality alpha may not be this value. Alpha may actually be alpha ij or alpha xy or alpha xz, depending on what direction, or alpha 1 or alpha 2. Okay, so based on different directions, like in the x direction alpha can behave differently, in the y direction it can have differently. So alpha can be, so for example, alpha x, alpha y, and so on. But because it is isotropic, it is assumed that the behavior will be same in all the direction, and hence you have only one alpha. Now this is because of only the thermal load. If you also have mechanical load over it, what do? You just superimpose them. So this is due to elasticity and this is due to the thermal part of it. So for example, you had the thermal strain X, that would be Ex. This can come from the Hooke's law, equation 5.2, and this Ex of T can come from over here. So the total strain, normal strain in the X direction for this solid at that point will be equal to this. Okay, so that is where we can study this, and you should also make a note of this, that if the material is rigidly constrained, I mean if you have this sort of a material and these are walls on both sides, so if the material is rigidly restrained so that no strain is possible, I mean it's a 1D element, okay, so there is no strain in the other direction. If the material is rigidly restrained so that no strain is possible, the elastic part of the strain will be negative of the thermal strain, since the total strain is 0. So because it cannot have any strain along the axis, so the elastic part, so Ex total has to be 0. That would mean that this part is negative of what this is under the action of both mechanical and thermal load. Okay, so that's how what will happen. So if you have any part of machine which is fixed like this 1D element, and there is a very large temperature change, so from T0 to T, it means that elastic stresses have developed in this which negate the strain due to the thermal changes. Okay, so that's where we end with this topic, and in the next class we will develop the complete equations of elasticity. I mean we have already actually developed, but we would just write it combining both the temperature and compatibility. So all of it will, basically all of what we have learned in this course will come together, and then we'll solve a couple of problems and see whether we can actually apply the knowledge which we have learned. So thank you.